Today we are going to discuss how to deal with the inequalities involving the side lengths of a triangle. Some standard inequalities like Cauchy-Schwarz inequality or AMGM inequality are already in our toolbox, which we use time to time. But if we want to deal with an inequality involving the side lengths of a triangle, then the story is different, because somehow we have to incorporate the constraints that the side lengths of a triangle must satisfy. And such incorporation is not easy until we take a resort in Ravi Substitution. Hello and welcome. Today we are going to discuss a great technique popularly known as Ravi Substitution to deal with the inequalities involving the side lengths of a triangle. We shall solve 3 examples to demonstrate this technique. Stay tuned till the end. Ravi Substitution is a technique which makes our life easy when we deal with the inequalities in terms of side lengths of a triangle. We cannot consider side lengths of a triangle just a normal positive numbers, because 3 positive real numbers can be a side length of a triangle if and only if the sum of any 2 of them is greater than the third one. In other words, if A, B and C denote the side lengths of a triangle ABC, then we have B plus C is greater than A, C plus A is greater than B, and A plus B is greater than C. So these are the constraints that side length must satisfy. If we are given some inequality to prove in terms of A, B and C, then we have to incorporate these 3 constraints, and believe me, they are not easy to deal with. Ravi Substitution is a savior here. By using Ravi Substitution, we can find another 3 equivalent constraints, and our new constraints would be very easy to deal with. To understand this technique, let's take an example. If A, B and C be the side lengths of a triangle, then prove that A over B plus C plus B over C plus A plus C over A plus B is less than 2. Since A, B and C are the side lengths of a triangle, so of course we have these 3 constraints. B plus C minus A is greater than 0, C plus A minus B is greater than 0, and A plus B minus C is greater than 0. As we already noted that these 3 constraints are not easy to deal with, we shall transform these constraints in some easy form. We introduce 3 variables x, y and z, which we let them equal to s minus a, s minus b and s minus c respectively, where s is the semi-perimeter of the triangle. Notice that x, y and z are positive real numbers. In fact, positivity of x, y and z is nothing but the equivalent form of 3 basic constraints in terms of a, b and c. The substitution x is equal to s minus a, y is equal to s minus b and z is equal to s minus c is known as Ravi substitution. The idea is that we can transform the required inequality in terms of x, y and z. For this we need to find the values of a, b and c in terms of x, y and z, and finding these values is an easy job. We notice that x plus y plus z is equal to s, and from the relation x is equal to s minus a, we get a is equal to s minus x, which is equivalent to a is equal to y plus z. Similarly, we obtain b is equal to z plus x and c is equal to x plus y. This is how we can express a, b, c in terms of x, y, z. Ravi substitution is powerful because we can transform some function f in a, b and c, which are the side lengths of a triangle, into some other function g in x, y and z, which are simply positive real numbers. In other words, we can transform the required inequality in terms of side lengths of a triangle into another inequality in terms of some positive variables. And of course, dealing with an inequality with positive variables is easy in comparison to an inequality involving side lengths of a triangle, because with positive real numbers we have some standard inequalities like AMGM inequality to help us. Let's come back to the problem. We have found the values of a, b and c in terms of x, y and z. This allows us to transform the required inequality in terms of x, y and z. To complete the solution, we need to prove this updated inequality, which we can prove by reducing the denominators of each ratio. In other words, we find 3 ratios which are slightly greater than the 3 given ratios. This gives us 3 inequalities, and by adding these 3 inequalities, we obtain the required result. This completes the solution. This problem was good demonstration of Ravi substitution. We saw how switching from sidelines of a triangle to positive real numbers is a useful strategy, thanks to Ravi substitution. In most of the problems involving the sidelines of a triangle, Ravi substitution is the most powerful tool because it transforms the variables denoting the sidelines of a triangle into some positive variables, which are comparatively super easy to deal with. As we said earlier, one reason that dealing with positive real numbers is easy because we have some standard inequalities like AMGM inequality to help us. Let's take an example which will demonstrate how Ravi substitution combined with AMGM inequality makes our life easy. If the perimeter of a triangle is 6, find its possible maximum area. We simply start with letting sidelines A, B and C and semi-perimeter S. We have A plus B plus C is equal to 6. That gives S is equal to 3. Since we need to maximize the area, so we write a function for area A in terms of sidelines A, B and C. This can be done by using popular Heron's formula. We have the area function A in terms of sidelines A, B and C. But as we already noted that sidelines are not easy to deal, so we again take a resort in Ravi substitution. So we simply let x is equal to s minus a, y is equal to s minus b and z is equal to s minus c, where x, y and z are positive for the same reasons as we have discussed earlier. So we get a is equal to square root of 3xyz with positive x, y, z and x plus y plus z is equal to 3. Now the problem boils down to maximize the square root of 3xyz, where x, y, z are positive with x plus y plus z is equal to 3. And this can be tackled nicely by AMGM inequality. So by using AMGM inequality, we get 1 as the maximum value of x, y, z. Hence the maximum value of the area is square root of 3. But technically we have to give a bit more details. We found the inequality that a is less than or equal to square root of 3. But from this, we cannot conclude that the square root of 3 is the maximum value of a unless we show there exists some positive x, y and z for which the equality holds. Since the equality holds in AMGM inequality when all the numbers are equal, so we see that the area attains its maximum value root 3 when x is equal to y is equal to z is equal to 1. Now we are safe to say that the maximum value of the area is the square root of 3. This completes the solution. This problem was a good demonstration of the strength of Ravi substitution. We saw how nicely Ravi substitution converted one function to another, which was super easy to deal with because we could be able to use ready-made AMGM inequality. We have already developed 3 videos on AMGM inequality. If you are interested in learning AMGM inequality in detail, you can watch them. The links are in the description. Plus, if you are interested in practicing more problems on Ravi substitution, you can refer our book Algebra Volume 2. The link is in the description. Let's take one last problem. In this problem, we will be using another ready-made inequality that is popularly known as Cauchy-Schwarz inequality. So let's go straight in the problem. If possible, try yourself first. Let A, B and C be the lengths of the sides of a triangle. Prove that A square B into A minus B plus B square C into B minus C plus C square A into C minus A is greater than or equal to 0. Determine when the equality occurs. Now we know the name of the game, Ravi substitution. We need to transform the given inequality in terms of positive x, y and z. And after some manipulations, we obtain the equivalent inequality. It means now we need to prove xy cube plus yz cube plus zx cube is greater than or equal to xyz into x plus y plus z, where x, y, z are positive real numbers. But this inequality too seems hard to prove. How should we tackle it? I don't get any immediate way, so let's tweak it with the hope of good. If we divide both sides by x, y, z, we get y square by z plus z square by x plus x square by y is greater than or equal to x plus y plus z. And fortunately, this is not a foreign inequality for us. We have seen this before. This is nothing but one and only one, the Cauchy-Schwarz inequality. More precisely, this version of Cauchy-Schwarz inequality is known as T2's lemma. We have 2 dedicated videos on Cauchy-Schwarz inequality and T2's lemma. You can find the links in the description. Since we have obtained a true statement by taking reversible steps, so this proves the required inequality. I repeat this point, it is crucial. We took some reversible steps and eventually we obtained a true statement. That was nothing but the Cauchy-Schwarz inequality. So this proves that the statement where we started was a true statement. This proves the required inequality. And from the condition of equality in T2's lemma, we get the equality if and only if x is equal to y is equal to z, and henceforth a is equal to b is equal to c. This completes the solution. Again, this was a problem where Ravi substitution made our work much easy. This problem was twofold. After Ravi substitution, we had to struggle to come up with the idea of Cauchy-Schwarz inequality. After all, this was an IMO problem. And believe me, this is one of the easiest IMO problem if we compare it with the recent IMO problems. That's it in this video. Next week we are going to see another amazing technique which is useful in finding the sum of series. And this is popularly known as telescoping sum. Thank you. See you next time.